This is Jack Jackson. In this video, we're going to be talking about sets of postulates for geometry, and we're going to talk about the synthetic versus analytic approach to geometry. First of all, let's start back at the beginning to Euclid. Euclid's postulates. The earliest set of postulates for Euclidean geometry are those given by Euclid in the Elements. We're going to go over each of these sets of postulates in their own videos in a minute, but I want to talk in general about some of these. They are listed below, translated from ancient Greek to modern English, and notice that they consist of 5 postulates and 5 common notions. These form the basis of Euclidean geometry, and all further studies of Euclidean geometry are consistent with this approach. And when we get to these in a minute, you'll notice that Euclid's 5th postulate stands out because it seems more complicated than the rest. Euclid took pains to prove as much as he could without using his 5th postulate, even when an easier proof existed using it. Only when he had exhausted these results did he resort to utilizing the 5th parallel postulate. Now, many mathematicians back in the day felt that one should be able to prove the 5th postulate as a consequence of the other results. If they would have been able to do this, then they would have shown that it was dependent on the other postulates, making it actually a proposition. Eventually, these attempts led to the discovery of hyperbolic geometry, in which Euclid's 5th postulate for Euclidean geometry is false, but the other postulates are true. This proves that the parallel postulate is in fact independent of the other postulates, thus vindicating Euclid's inclusion of it. Yeah, he was right all along. He needed it. However, as time went on, mathematicians found that Euclid was actually assuming some additional postulates which he did not explicitly state. So David Hilbert is often regarded as the greatest mathematician of the 20th century. Among his many achievements was the establishment of a set of postulates for Euclidean geometry that meet modern standards of rigor and fill in the gaps missing in Euclid's approach. Still based on basically Euclid's approach, but just making a little bit better. Hilbert's axioms for Euclidean geometry are also listed. We'll go over those in a couple of videos from now. Both Hilbert and Euclid studied Euclidean geometry using what's called a synthetic approach. When using a strictly synthetic approach, numbers and measurements are left out of the study as long as possible, except for rational numbers. We can count things, but otherwise we leave out numbers. So with the strictly synthetic approach, no properties of real numbers are assumed, only the properties of rational numbers are assumed. If one is very careful and rigorous, eventually one can actually derive the properties of real numbers from Hilbert's axioms. A slight variation on the axioms of Hilbert is to replace the side-angle side triangle congruence postulate with a postulate that guarantees that a reflection preserves congruence. This approach is featured in the work of Zaluziskin, among others. With this approach, one emphasizes transformations much earlier and throughout the development of Euclidean geometry. Many high school textbooks take this approach. And we will not take this approach because including the SAS postulate fits nicely into a study of neutral geometry, including Euclidean and hyperbolic geometries, much more easily, whereas it is much more difficult to study transformations in any kind of unified manner. So in our last unit on Euclidean transformational geometry, we will be focused just on Euclidean geometry, and then we'll show that these two possible postulates are logically equivalent to each other if we assume the other postulates of Euclidean geometry. I want to also mention Burkhoff's axioms. In contrast, G.D. Burkhoff established a set of axioms for Euclidean geometry using an analytic approach. We'll go over those in another video in a bit. In Burkhoff's analytic approach, all of the properties of real numbers are assumed. The axioms then establish correspondences between real numbers and points on a line, and between real numbers and angle measures. And using these properties of real numbers, the axioms of Hilbert could then be proved as propositions. And doing it this way, actually Burkhoff is able to narrow it down to just a very few axioms. But it takes on a completely different flavor because everything's based on the properties of real numbers. Now, let's talk about a hybrid approach. For this class, we'll be using a set of axioms or postulates which follow a hybrid approach. So we're going to have our own set of axioms here. In this approach, we will mostly be following postulates similar to those of Hilbert, so that the synthetic approach will mostly be preferred. However, we will also assume a couple of analytic axioms like those of Burkhoff, so that early on we can talk about measuring line segments and angles. Using this approach, between becomes a defined term, where it was undefined in Hilbert's axioms, and Hilbert's axioms of betweenness will actually become propositions in our geometry. Our approach produces a set of postulates that are not all independent, but this hybrid approach gets us into an important concept of measure early on. It speeds up our development considerably in a few places. Okay. So our set of postulates for unified geometry, which includes Euclidean and hyperbolic geometry, and for as long as possible, spherical geometry and taxicab geometry, these are chosen so that we can study these four geometries simultaneously. And this allows us to compare and contrast these four geometries while also making clear what propositions are consequences of which postulates. The set of postulates we will use are closely based on a hybrid approach set of Euclidean postulates from Boyes in his text, Elementary Geometry from an Advanced Standpoint, and also on the postulates in our textbook, Kay's College Geometry, a Unified Approach. We will give the first section of these postulates in a bit, in a video of this playlist, in the first week of the geometry class, and then we will prove what we can using only these postulates, and then we'll add further postulates, definitions, and propositions each week for several weeks as we build up our geometry.